Welcome to our lecture online. Here we're going to answer the question, what makes a nebula collapse into a star? It's not something that happens readily, because if it did, all the nebulas would have by now have become stars and no new stars would be born. And we know that star formation is still going strong in many galaxies of the universe. So we know that it does take very special events and very special circumstances. But here we're going to look at some basic principles. And then later on we'll of course explore what some of the catalysts will be for the collapse to begin, because normally nebulas do not just readily collapse into stars. So if we assume that this sphere here represents a nebula, and we'll take a gas molecule at the very edge of that nebula. Notice the mass, the gas has mass big M, and the molecule has mass little m, and the radius is the distance from the center of the gas, or the center of the nebula, to the edge where that molecule resides. Now that molecule will have some velocity v. That means that the kinetic energy of that molecule will be 1/2 mv squared, or we can then say that the velocity is equal to the square root of 3kT over m. Now k is the Boltzmann's constant, which is essentially the gas constant divided by Avogadro's number, which is 1.38 times 10 to the minus 23. And T is the temperature in Kelvin, and m is the mass of the molecule. We can also write it in terms of the gas constant and the molecular, or the molar mass, I should say. The potential energy of this particular molecule will be minus g times the mass of the gas times the mass of the molecule divided by the distance of the molecule from the center. So that the entire nebula is affecting gravitationally that small molecule at the edge. So we can also write the kinetic energy if we replace v squared by 3kT over m. And therefore we get 1/2 mv squared is 1/2 m times 3kT over m, which is 3/2 kT. So that's another way of expressing the kinetic energy of the molecule simply in terms of the temperature and the Boltzmann's constant. In order for the molecular cloud to contract, the kinetic energy of the molecule must be less than the potential energy. And this is really the key of understanding of how a molecular cloud, or how a nebula collapses into a star. And of course that needs to be true for all the molecules on the edge of the nebula and within the nebula as well, because we can take a molecule like inside the nebula, draw a sphere relative to that distance and do the same calculation. So all throughout the nebula we have to have the condition where the pull downward from the potential energy is greater than the energy the molecule has in the kinetic energy. So we want 1/2 mv squared to be less than the absolute value of gmm over r. If we then get rid of this mass of the molecule, we can calculate v to be needing to be less than the square root of 2gm over r. Now we can find the orbital velocity, which is the square root of gm over r, and we can do that by setting m times let's see here, m times g equal to gm big M over r squared, so that the force of gravity is equal to gmm over r squared. And let's see here, no, that's not the equation that I want. What I do want instead is this equation. If something goes around in a circular path, we know that the force, the centripetal force, which is caused by the force of gravity, which is force of gravity, which is equal to g little m big M over r squared, that must equal to the centripetal force, which is mv squared over r. If we solve this equation for v, we get the orbital velocity. That's what I was trying to find. All right, now we see that the orbital velocity is a little bit less than this equation right there. But then we realize that the escape velocity is equal to the square root of 2 times the orbital velocity, which is equal to this, which is exactly what we had there. In other words, for a cloud to collapse, what we want is the molecules on the edge to have less than the escape velocity so that they will be pulled in. So essentially, you want the velocity of the molecules, wherever they are, to be less than the escape velocity at that particular position. And that's the basic principle, the basic condition that you must have in order for the collapse of the nebula. And that's how it all starts. That's how the stars are formed once the conditions are right for the collapse of the nebula.